Hello and welcome to Knife Based Classifier Explained for Beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this particular video we are going to talk about knife based classifier. In particular, we will talk about Bayes' rule, which is the foundation of supervised learning in most of the cases, whether you are going to deal with the supervised learning in a discriminative way or a generative way, one way or the other. The foundation is set by the Bayes rule. We will see that applying Bayes rule directly on data may have certain issues, and one very potential issue is curse of dimensionality. And there are several ways of handling with curse of dimensionality under a lot of assumptions. One such assumption is the knife Bayes assumption. And this is the assumption because of which the whole classification scheme is referred to as knife Bayes classifier or classification scheme. We will also extend our knife Bayes assumption towards the regression task, and finally we will wrap up our video with hands-on implementation in Python in scikit-learn for knife Bayes classifier for text data. If you are a consistent viewer of AI Sciences, you're going to enjoy this knife Bayes classifier as well as you are already enjoying a lot of our tutorials and videos that are there on our channel. And if you're new to AI Sciences, then welcome to AI Sciences. At AI Sciences, we deliver artificial intelligence and data science courses, consultancies, and tutorials. And please subscribe our channel. You're going to enjoy the world of data science with AI Sciences, along with a lot of hands-on practices in Python, tools, and state-of-the-art implementations and state-of-the-art kind of theoretical aspects of data science. So let's start. Bayes rule, let me explain Bayes rule in terms of the classification first. And let's take an example that we have some data with features, let's say x1, x2, x3, x4, x5, x6. These are features. And this y is basically the target label. And target label in this case is just binary, which means we have just two classes, class 0 or class 1. Here we have 24 different examples, data samples, and 6 features. So the Bayes rule can be explained or can be derived in a very easy way, although its derivation is much simpler, but its applications are much wider and very deep. So the Bayes rule says that the probability of a class y given the data sample x is equal to the probability distribution of the target into the probability distribution of the features in the class divided by the marginal distribution of the features. By the way, if you do not know the theory of probability, we strongly refer you to go to our YouTube channel and go through the probability basics of probability. We have already posted that there, and also we have a full course mastering probability and statistics in Python on AI Sciences. So please see the links below in the description, and you can just have a very good practice of what do we mean by probability and all these theoretical aspects. So here in this video, I'm assuming that the reader has some knowledge of probability theory already. So that's the Bayes rule, and what it says is following. If we describe this x as a vector of these features, let's say x1, x2, x3, ... x6, and a particular sample can be described as following. For example, the sample, let me describe the sample number 9, that is 41, 41.41, then 35.41, minus 35.41, and then we have 49, where was I? Yeah, 49.692, and then we have 61.1212, 61.1212. So that is xi, where here I is 9, so that is x9. and the corresponding yi, which is y9 in this particular case, is 0. Yeah. So the goal of Bayes rule is to find out the probability that y is 0 given that the x is xi. And that can be accomplished by having all these different components on the right hand side, and each component on the right hand side indeed is a probability distribution. So that's the goal. First, if we can find out the probability of y is equal to 0 given that, and then if we can find out the probability of y is equal to 1 given x is equal to xi, then the classification happens by choosing the max of these probabilities, whether the max goes over 0 or 1. So that's the basic Bayes rule. The problem with the Bayes rule, not just the Bayes rule, the problem in general in probability distribution mostly lies in this particular case, mostly lies in this part, which is sometimes known as class conditional distribution. Although if we are going to just classify and we do not care about whether the resulting whether the result is a valid probability distribution or not, we can discard the denominator because that is common for both of the classes. And if you're going to choose max, that common denominator is not hurting whatever the max is. So the real goal is to estimate the distribution of classes and the distribution of features in the classes. So these two components. And the problem really is when we have large number of features. For example, consider we have only one feature, let's say x1, then that's a one-dimensional problem to estimate. So the probability of x1 given the class y is equal to 0, that is one kind of distribution. Probability of x1 given y is equal to 1, that's another kind of distribution. So we can estimate these distribution quickly, and there are several ways of estimating distributions. Again, I refer the reader to our full course on probability and statistics. That is, the link is in the description below. What happens is if you have only one feature, then you do not need a lot of data points to estimate the probability distributions reliably. I mean, a few data points, maybe on the order of hundreds or maybe thousands or maybe smaller or larger depending upon the complexity of the problem, can work very well. But what happens is if your number of features are getting larger, then the space in which you are going to estimate this probability distribution function, that space actually becomes larger and larger. And to estimate the distribution of data in the bigger space, you need several data points, a lot of data points in a bigger space to estimate this function reliably. So that is one function. Another function is x1, x2 given y is equal to 1. And it becomes further severe if your data points if your features become further larger. If your features are, more than 2, 3, then the space of these features, sometimes called the feature space, becomes so large that the number of data points needed to estimate these functions reliably, for example, x1, x2, x3 given y is equal to 0, and similarly for y is equal to 1, the two functions. To estimate these functions reliably, these probability distributions reliably, you need a lot of data points, And that grows on and on and on as we have many more features. So this actually refers to, technically, it refers to as the curse of dimensionality. Dimensionality means the number of features, and the dimension of feature space is actually the number of features, and which sometimes loosely referred to as the size of feature space as well. If your feature space is high dimensional, which means your number of features are many. In this particular case, our feature space is 6 dimensional because we have 6 features. If your number of features are large, many more, then the number of data samples required to estimate this class conditional distribution is very, very large. In this particular case, the number of data samples are just 24, going from 1 to 24 data samples. But if your number of features becomes large, then the need of the number of sample points that increase exponentially with the dimensions of the feature space. And that's a big problem, because then estimating this joint distribution becomes a big hurdle, because availability of the data compared to the presence of the number of features in the data, that availability of the data, the sample points, is not guaranteed. And in many cases, the features are on the order of hundreds and even millions today. And the data required to estimate these probability distributions reliably, that availability of data is not always guaranteed. So that's a big problem to estimate this joint distribution. To handle this problem, there are several ways, and one way is to assume that different features, they are independent in a particular class. That is called conditional independence. So think about A as x1, so this is x1, and B as x2. Rather than estimating a joint distribution in the space of x1 and x2, what we can do is we can estimate the one-dimensional distributions individually, and with the assumption that the two features are independent in a given class, the joint distribution indeed is equal to the individual distributions. And what happens is each individual distribution is a single dimensional, and so that single dimensional distribution estimation becomes really simple and faster. So that's the basic assumption, which is known as the naive Bayes assumption. The assumption is the features at hand in a particular class, they are independent. No pair of features, they depend upon each other. What it really means is that given the value of x1, let's say 5.3, we can have no idea of value of x2. So having known that, for example, in class 0, if the feature x1 has value 5.3, this information that in class 0 the feature 1 has value 5.3 has no impact whatsoever, and we have no judgment at all to find out the value of x2. And vice versa, if you have for example the value of x2 in a particular class, then you have no idea to judge the value of x1. And that is true for all different kind of features. For example, if you have several features x1, x2, x3, x4, and so on, they're all conditionally independent. With this assumption, the probability distribution, the joint distribution estimation, becomes simpler, but then there is a question whether this assumption is realistic or not. Well, the assumption, I would say, is not realistic. In several cases, the features are really dependent. That's the theoretical side of naive Bayes. But what happens in practice is this assumption works very, very well in practice in most of the situations. And also, to handle curse of dimensionality, one way or the other, we have to impose some kind of assumptions. And this criticism that the assumption is valid or not goes for those criterion as well. So theoretically, the assumption is not always valid. It is not a realistic assumption, but practically it makes things very, very fast. And in most of the cases, this assumption is, even though it doesn't seem like a realistic assumption, the results are really promising and it works really, really well. One final note, right now we discussed everything in terms of discrete features. So for example, if we have discrete features, we are going to estimate the probability function, which might be a PMF or probability mass function. In case of target label, which might be a continuous value, and in case of the features, which might be the continuous features, we have to estimate density functions rather than mass functions. So the density function Bayes rule, or in the form of continuous target and the continuous feature, the Bayes rule looks like the following. And the naive Bayes assumption is just as follows. Here the only difference is f referred to as the continuous distribution and p referred to, and the p, as you've seen here, referred to as the discrete distribution. And once we have this density function estimated, then the regression value for a particular y given x can be estimated as the expected value of this random variable y, as long as this y is a continuous random variable. So that's it about the theoretical part of naive Bayes. Let's go through a simple example in Python to actually see what is there available in scikit-learn for us in terms of naive Bayes. So I have here an example of topic identification for you. And the data set we are using is the 20 news group data that is there in scikit-learn.datasets. We will convert the text data into the feature vectors, and right now we are using term frequency inverted document frequency index vectorizer. For those who want to understand what do we mean by feature extraction and feature engineering, I will strongly recommend you to take our course on feature engineering. And please see the link below and you will be having a very good idea how to convert the real data to the feature data that is required for machine learning algorithms. So these two are required for feature extraction. And then we will be using Gaussian naive Bayes. Oh, I just skipped one of the things, one of the very important things. By the way, the assumption of this, the assumption about the type of this individual models, either these are density models or these are probability mass functions, whatever these are, the assumption that what type are these and in what way we are going to estimate these probability distributions, based on these kind of assumptions, the naive Bayes classification or regression scheme actually vary. One can think of that all these individual items, they are Gaussian distributions. And so the final distribution, which is the multivariate Gaussian, actually depends upon the individual Gaussians. One can think of the individual distributions to be having some other family of distributions and may not be the same family. They may belong to different families. Depending upon how these individual distributions are estimated, the naive Bayes have different variants, although the basic assumption at the back end is the same, that the features in a class, they are independent. So here we have taken the assumption that all the individual components are Gaussian, and hence we have Gaussian naive Bayes that is already there in the scikit-learn package. So let's load that. Here we have loaded the training data. That's a function that will help us loading the training data. And this is a function that given the training data, it will return us the model for extracting the features. So it first built a count vectorizer for counting different terms, and then TF-IDF transformer to actually convert the counts to their TF-IDF feature vectors. And it returns these two transformers to be used to compute features whenever required. So that's the function that actually is used for computing features, that uses the model that is there in the build feature model. It actually, given the documents in the form of text, it converts the document to the counts and then apply the TF-IDF transformer to convert it to the feature vectors. From the data, let's pick some topics. By the way, this whole notebook is for topic identification or topic classification. So given a text, we want to find out what is the topic of the text, what is the goal discussed in this text. So let's have some categories, let's say atheism and religion and graphics and medicine. Let's load the data from these categories. The data is loaded. Let me just show you some data here. Let's say if you see this data snippet, that's the data given, and this data has the label atheism. Now, once we have all that data, let's build the feature model. This is the count transformer. This is the TF-IDF transformer. And once we have these two transformers, we can convert our data to features. Let's see. Here, it may take a few seconds because this feature extraction is a costly process. Now, if you see that our data has 2257 documents, and the feature space is actually 35,788 dimensional. That's the size of the features, the total number of features, which is huge. Now you can think of estimating a joint distribution in that big feature dimensional space is really I mean, difficult or I mean, it requires a lot of data on the other hand, and has computational issues and a lot of other computational aspects. Now let's fit the knife-based classifier on our data, and these are the targets. That's the supervised learning task. The knife-based classifier is being fit on that. Once we have fit the model, let's classify different documents. Let's say this is a document having God is there. Another document, let's say OpenGL works very fast, and the other document, no one is there. For example, these three are the documents, and we want to check the topic in these documents. By the way, these are the documents that we have just written, and they are not there in the training data. First, we compute the features of these new documents using our count transformer and TF-IDF transformer. Then we predict the topics using the knife-based classifier.predict function, and then see what is the target, that is, what is the predicted value that is returned by the knife-based classifier. So as you can see here, God is there. The topic knife-based came up with this atheism. God is there. Maybe it is religion, but it turns out to be atheism. OpenGL work fast, that is computer graphics. No one is there, that is again atheism. If we say, for example, God loves everyone, let's say, that may turn out to be religion. So, for example, God loves everyone, that turned out to be, the topic turned out to be religion as compared to atheism. So that was a quick walkthrough of the knife base, particularly the Gaussian knife base, using in scikit-learn for topic identification. I guess you have enjoyed this video. Please subscribe our channel, like this video, and share this video with your friends. And please see the links in the description that will help you following a lot of data science and artificial intelligence courses and consultancies that you may have required in the domain of data science. Thank you. Hope to see you next time.